Good morning, students. Today we'll be seeing the video on ARM7 Interrupts. Okay, so interrupts is otherwise known as exception. So last video we have seen about the 7 operating modes of ARM7 processor. So just a little history about the interrupts or exception. Here you can see that this is the first computer that started the exception handling. This was a computer that was introduced in 1953, and this computer is called UNIVAC, which is Universal Automatic Computer. Okay, so that is why I have just added this picture here on the first slide. So this was the first computer where exception handling was introduced in the year 1953. So we have gone a long way, and we are going to see what are the interrupts that are involved in ARM7 processor. So coming to the before we see the interrupts, we have already seen the operating modes of ARM7. So these are the 7 operating modes. Okay, we saw that in the previous video. You might think that there are 7 operating modes, and so there are 7 interrupts. So all 7 operating modes are entered using the 7 interrupts. No, that is not the truth. Actually, only 5 operating modes are entered using interrupts, that is supervisor, abort, undefined, IRQ, and FIQ. And user mode and system mode do not have to be entered via an interrupt. Okay, so that is what I have given in the tip here. So there are 7 interrupts in 7 modes, but not necessary that each interrupt is involved with one mode. User mode and system modes are not entered by an interrupt. So let's see how these modes of operations are related with the interrupts one by one. So any processor, the first interrupt and the highest priority interrupt is the reset interrupt. So whenever a reset interrupt occurs, we enter into the supervisor mode, right? We have seen this in the previous video also. And we have one more interrupt that helps you to enter into the supervisor mode. That is called the software interrupt. Now the difference between this reset interrupt and software interrupt is reset interrupt helps you to directly go into supervisor mode. That is when you reset a system or when you start a system, directly it enters into the supervisor mode. But whereas the software interrupt also goes into supervisor mode, but then when you are working in a user mode and when you want to shift to supervisor mode, you use the second interrupt, software interrupt, SWI. So we have seen 2 interrupts. The third and fourth interrupts are related to the interrupts request. So if you have a normal interrupt request, you have IRQ as an interrupt. If you have fast interrupt request, you have FIQ as an interrupt. So that is the 4 interrupts for you. Now, when you have abort issues, that is either you are trying to access the system program or system data from the user mode. Okay, as we have seen in the previous video, either it can be a prefetch abort where you try to access the system program, or it can be a data abort where you try to access the system data from the user mode. So these are the next 2 interrupts that are involved between the user mode and the abort mode. So whenever these 2 interrupts occur, immediately you are shifted to the abort mode if you are in the user mode. And then you have one interrupt related to the undefined mode. So undefined is the name of that interrupt. So you move from user mode to undefined mode. So that sums up to the 7 different interrupts. So the 7 different interrupts are the first is the reset, then software interrupt, then you have IRQ and FIQ for answering the interrupts, then you have prefetch abort and data abort for entering into abort mode, and you have undefined for entering into the undefined mode. But there are no interrupts involved for entering from user mode to system mode. This happens automatically. Okay, so this you have to understand. So there is no interrupt to enter into system mode, and there is also no interrupt to go into user mode. All interrupts are generated by user except reset. All other interrupts are generated by user, and to enter into user there is no special interrupts available. So this is about the 7 interrupts of ARM7. Now moving on to the vector address. We have seen in 8051 also that whenever there is an interrupt, that is your memory, okay, your 4 GB memory in ARM will be allocated some spaces. Say, for example, if you go to this memory location, you will have a set of instructions that will say how that interrupt has to be processed. Okay, and that starting address of that memory location, you call it as vector address. We have seen this in 8051 also. So like that, you hear the 7 interrupts: supervisor, undefined, and then sorry, reset, undefined, software interrupt, refetch abort, data abort, IRQ, and FIQ. All the 7 interrupts, they have their own vector address. This is a starting address for their uh, vectors. Okay, vector and set of ISRs. So here in ARM, in 8051, we have seen that there is only one single vector address, right? For every interrupt, there was one vector address. But here we can see that there are two vector addresses for the same interrupt. For example, reset. Reset, usually for any processor, the vector address of reset will be all zeros, because that should be the first program that should be running for a processor. So it is always all zeros. So whenever why is that there are two vector addresses here in ARM7? So here you can see one vector address is called normal vector address, and the other vector address is called high vector address. Now the reason is you have a 4 GB memory, right? Now come on, tell me, where are those in your ISR stored? ISR is nothing but you have an interrupt. So immediately you have to move from your user program to the interrupt. Okay. So when you go to that interrupt, you will have a set of programs. When you execute those programs one by one, which means you are answering the interrupt. And last line of that interrupt service routine will be written. So you return from the interrupt to the normal program. This is what usually happens. Now, why is that there are two vector addresses here in ARM7 is because now tell me whether this interrupt programs should be stored in RAM or ROM. Yes, it has to be stored in ROM, because whenever you switch on and then switch off the processor once again, these interrupt instructions should be remaining there permanently. It cannot be deleted or it cannot be removed and all that. It has to be remaining there permanently. So if anything that has to be remaining permanently, it has to be stored in the ROM memory, right? Not in the RAM. So here there are two ways this ROM can be allotted. This is like the entire 4 GB memory is there. You have to allocate. This part of the memory will be used as ROM. This part of the memory will be used as stack. This part of the memory will be used for some other purpose. Like that, you have to allocate the memory. So here in this case, you can allocate the memory in two ways. Suppose this is their entire 4 GB memory. The lower portion of that memory can be allocated as ROM. In that case, your vector address that you use will be normal vector address. That is why you can see that your starting addresses are all 0. That means the lowermost, so this is like 0000 to FFFF. So when you allocate the ROM to the lower order address bits in the memory, then you use the normal vector address. You can also allocate the ROM to the highest order addresses of the memory. So in that case, your ISRs will be stored in the FFFF location. So that is why you have an option. In some processors, you can allocate ROM to the lower order address bits. So that means you'll be using the normal vector address. And in some ARM processors, you can, depending on its application, okay, you can also use the higher order address bits of the memory as ROM. So in that case, your vector addresses will be starting with FFFF. Okay, so that is the reason why your ARM processor has got two vector addresses. One is normal vector address and the other is high vector address. So both will not be available. If it is normal, all interrupts will be normal. If it is high, all interrupts will be high. I hope this is clear. So that is about why we have two vector addresses in ARM. Now, coming to the the vector address locations, you can see that the first vector address is reset, which is 00000000. It is the 0th location. The next one is the 4th location. The next is the 8th location. Then you have the 12th location. Then 10, 14, 18, 1C. Okay. So now here, in between every interrupt, there are four locations, right? You have a space of 4 locations. Can you tell me what is the reason? Yes, we have been discussing about this reason from the first video onwards. We know that every instruction in ARM is 32-bit. So 32-bit means it occupies 4 bytes. So 4 bytes means 4 locations in the memory, right? So this is 1 byte. So that is zeroth location. Then 1, 2, 3. So 0, 1, 2, 3 will be the location where you have your ISR starting address of reset. Getting it? So that is the reason that it occupies 4 locations evenly, because all instructions in ARM are 32-bit. Now, can I explain the entire reset operation within this 4 location? It is not possible. So this vector address is just, it is like you have a reset. Suppose you're working in a user mode. You're getting a data abort interrupt. Okay, so what happens? You immediately move to the vector 00000010. That is the data abort vector address. Suppose you're using a normal vector address. Okay, so now this vector address is just it's like just a path for you. So from here it will be directing you to the exact location in the memory where you have the instructions to run the data abort. Are you getting it? So this is just a branch instruction starting address. So when you are in user mode, suppose you get a data abort, immediately you are moved to the location 00000010. Then this 00000010 will take you to the location where your abort program is actually stored. The reason why this is done is because for some applications, data abort program may be small, so maybe just occupying a few space in the memory. For some applications, data abort may be a huge program. Okay, so I cannot evenly give some space for writing data abort instructions, because it depends on what kind of application it is. For example, when you take a reset, if you have a ordinary TV remote, the reset program may be just a very minute, very small program. But suppose you take a high-end mobile, the reset itself will have many instructions, so it will take some time for the reset of a mobile to run. So I cannot allocate a common space for every reset program. So depending on the applications, the interrupt program size will vary. So that is why this vector address will direct you to that particular interrupt. I hope it's clear. And so this is about the vector addresses of the 7 interrupts. So 7 interrupts take you to the 5 modes. The 5 modes are supervisor, undefined, abort, IRQ, and FIQ. And system and user mode do not have an interrupt. Clear? Now moving to the next one. When an interrupt occurs, what are the steps? This is very important. That is how you will be executing an interrupt. Okay, now suppose you are in user mode and undefined interrupt occurs. Okay, and what is the step-by-step process that you will have to carry out for answering that interrupt, and then how will you come back again to the user mode? So this is what we call it as interrupt service routine. So let's see what are the steps involved in interrupt service routine. The first step is whatever is the current program that you have been running. Okay, you have to complete the execution. Suppose you are in the fetch phase or in the decode phase, or even maybe in the execution phase, you have to complete whatever instruction you have been running. So that is the first step that you will be doing. The next thing is your CPSR, that is your current program status register content, will have to be taken and saved into SPSR. We know that SPSR is a banked register. That means every mode has their own SPSRs. Now I told you, suppose it is a undefined interrupt. Then you take the CPSR and then store it into SPSR of undefined mode. Okay, we have seen that in the register programmers model. So this is a banked register. The third thing is we have to change the mode bits of CPSR. Why? Because we were earlier in user mode. Now we are moving into undefined mode. So undefined mode, the 5 bits, okay, the lower order 5 bits of CPSR is different for user and different for undefined. So you have to change the mode bits. Then your PC, okay, whatever is your PC content, because your PC will be pointing to the next instruction, right? You suppose you were executing ith instruction, your PC will have I plus 1. So this I plus 1 content from PC will have to be taken and loaded into your link register. Now again, this link register also is banked, right? So suppose you're moving into undefined mode, your undefined mode will have its own link register. So you have to load the PC content into link register of the undefined mode, okay, to the corresponding mode. Similarly, the next thing will be all the banked registers are changed as per the mode. That is, whatever register contents you want to store them, you have to store them either into a stack or keep them safe so that when you come back, you get all the register values. Okay, and suppose if it is FIQ, you have banked registers, that is R8 to R12, 8, 9, 10, 11, 12. The 5 registers are used specially when you're entering into the fast interrupt mode, right? So these banked registers are changed as per the mode. And as I told you, the when you just load the PC value into LR, your PC is safe now. Now your PC should be loaded with what you should do, right? So what you should do, you should be having the ISR address. So ISR address is interrupt service routine. Interrupt service routine has to be loaded into your PC. So then your interrupt will start being executed. So this is the 6 major steps that you have to go through whenever you are moving from your user mode to any one of the other modes of operation by means of an interrupt. So whenever interrupt occurs, you have to carry out these 6 steps. Now you have your PC loaded with your interrupt service routine address. So what you do, you go there to interrupt service routine. It will have a few set of instructions, right? So fetch them, decode them, execute. Then again fetch the next one, decode, execute. So this is carried out in a normal way. But please remember one thing. In your, when you're executing a normal instruction, okay, that is not interrupt instruction but normal instructions, you can do it in 2 modes. Either you can have it in the ARM mode or thumb mode. ARM mode means all instructions will be 32-bit. Thumb mode means all instructions will be 16-bit, right? But whenever an interrupt occurs, okay, your interrupt instructions cannot be executed in 2 modes. There is only one mode for your interrupts to be executed, and that is only ARM mode. There is no thumb mode for interrupts to be executed. So all your interrupts are only 32 bits. You're getting it? I'm repeating it. Your normal instructions can be executed either in your ARM mode or thumb mode, but your interrupt instructions should be executed only in normal ARM mode, cannot go into thumb mode. So whenever even if you're working in a thumb mode, okay, suppose you get an interrupt, then you have to change the mode from thumb mode to normal mode and then go and execute the instruction and come back. So this is something that you should understand very clearly in case of ARM processors. Now you have gone into the interrupt service routine, you have executed. So what will be the last instruction for an interrupt service routine? Yeah, it will be a return instruction, right? So now what are the steps that you have to do whenever you have to return from your interrupt service routine to the normal program? Let's see. So this is simple. First thing is you have to take your SPSR, saved program status register, of that mode, whichever mode you have gone into. Suppose undefined, you take the SPSR of undefined and put it back into CPSR. Okay, so this is the first thing that you should do so that you get back all the status bits and all that to run the normal program. Then you have stored your program counter value into a link register. So take the content from the link register and put it back into program counter. This is the return address. So you are now going back to the I plus 1 instruction. Getting it? And the third important thing that you should do is all your banked registers should be restored. Okay, suppose you have gone into FIQ mode, you would have gone into R8 to R12 banked registers. So you have to restore back into your normal user registers R8 to R12. Okay, so this is the 3 steps that you have to carry out whenever you complete an instruction and then come back to the normal program. Now there are 7 interrupts, but suppose there are 2 or 3 interrupts that occur at the same time. Okay, so we always have to prioritize the interrupts, right? So how is the prioritization happening in ARM7? So this is a priority for you. In any processor, usually reset is given the highest priority. So that is non-maskable usually, and it is given the highest priority. So even if reset and FIQ happens at the same time, the first priority would be given to reset. And then data abort is given the second priority, because I told you prefetch abort and data abort is something concerning our security issues. So suppose if a user is trying to access the system data, okay, so that cannot be allowed, and you cannot give the priority to some other interrupt and allow the user to try going into phishing into your system data. So that is given the very highest priority. So suppose you are saving some passwords, some sensitive data, nobody should be able to hack those data. So data abort is given the second priority. And of course, fast interrupt is given third priority, because that is the fastest interrupt compared to IRQ. And then IRQ is given the fourth priority, and prefetch abort is given the fifth priority. The reason why this is given fifth priority is because you are only trying to access the program, okay, not the data directly. So if it is data directly, it's going to be more a serious issue. So that is why that is given a second priority, and prefetch abort is given the fifth priority. And undefined and software interrupts both are given the lowest priority and the sixth position. Why 2 interrupts are given sixth position is because these 2 interrupts cannot occur simultaneously. If there is an undefined interrupt, software interrupt cannot occur. If there is a software interrupt, undefined interrupt cannot occur. So there is no possibility that these two will occur simultaneously. So that is why both of them are given the lowest priority, and it is 6. So this is about interrupt, my dear students. So we have seen in today's class the how the 7 interrupts help us to move into the various modes of operation. So 7 interrupts help us to move into 5 modes of operation. So if there is an interrupt, you go into either FIQ or IRQ. If there is abort issue, we go to either, it can be either prefetch abort or data abort, you go into abort mode. When you have an undefined instruction, you go into undefined mode. And whenever you have to go into, supervisor mode, you have 2 interrupts, reset and software interrupt. So reset happens automatically, and software interrupt is you move from user to your supervisor mode. Okay, and for entering into system mode and for coming back to user mode, you do not have any interrupts or exceptions. So that's it about the interrupts of ARM7. Hope it is clear. Thank you.